walk a long distance from the King's building to this wonderful institution. And again, I thank organizers for inviting me. But what I want to talk about is really also open questions about the Landau level near half filling. And originally I was thinking of, well, there's just basically two topics I could be talking about here. Both of them are related to particle hole symmetry or lack thereof near a half-filled Landau level, and one of them is what happens near nu equals 1/2, that is when you're in the lowest Landau level, and the other thing, which is also, as you heard, very poorly understood, is the nature of the even denominator fractional quantized Hall state that's been observed at 5/2. Now, I'm not going to say much. I'll just say a couple of words about that because that was so beautifully covered by Dima. And so I'm going to emphasize the first topic, and it's somewhat of a bunch of detailed questions about what happens in that situation. So again, centered to this is particle hole symmetry, which Dima alluded to, but didn't say too much about. The point is that if you have if you have a bunch of interacting electrons in a magnetic field in 2 dimensions, and if you take the limit where the mass of the electrons goes to 0, let us say, which drives the cyclotron energy to infinity, keeping the magnetic field fixed, but keep the electron-electron interaction constant, then what happens is that you can neglect any kind of mixing between Landau levels. If the Fermi level is in the middle of, say, the second Landau level, scattering events can create particles holding the second Landau level, but they won't create any mixing between the other Landau levels. And then and also if we neglect spin, we say only one spin state is occupied because it's a strong Zeeman field, and there are only two-body interactions, then it turns out there's an exact particle hole symmetry between states at a filling fraction nu in the Landau level and 1 minus nu in the same Landau level. There's a one-to-one correspondence of energy levels, energy gaps, and similarly for transport properties, there would be a complete symmetry. And of course, you could say, well, what happens at nu equals 1/2 when it maps into itself? Well, there are also consequences if you're looking at a state that's self-similar, that also puts restriction on, say, what various things that can happen. Now, of course, a real system will have some Landau level mixing, and Dima was arguing that maybe that this is a really big effect in the second Landau level. Maybe it isn't, or maybe it is. But for my purposes, I don't care that much about that because a Landau level mixing, it's certainly a good starting point, at least at the lowest Landau level for discussions. It seems to work actually quite remarkably well. But even if it didn't, if we're looking at theory, we should be able to handle this limit. A good theory should be able to describe this limit appropriately. And that's where the questions arise. Again, just to say, in the lowest Landau level, remind you what actually does happen experimentally. So there's no evidence for a quantized Hall plateau at nu equals 1/2, the lowest Landau level, and therefore there's no no evidence for any kind of energy gap in the ideal system. The the longitudinal resistance is just continuous. It's finite and varies continuously, depends on the sample quality. And as I said, of course, the Hall resistance also varies just continuously with magnetic field or filling fraction. But it's not that it's a completely uninteresting state. We know that there are interesting things that happen. For example, there are anomalies that were observed in the propagation of surface acoustic waves observed by Willett et al. In 1990, which showed us that something interesting was happening. And of course, we tried to explain this using basically what I call a fermion-Chern-Simons picture, but it's basically based on the composite fermion picture of Jnanendra Jain, which is really a common starting point for describing almost everything that goes on, at least in the lowest Landau level. This was something based on trial wave functions, and this was reformulated by Lopez and Fratkin, not in terms of trial wave functions, but in terms of a bunch of non-relativistic fermions interacting with a Chern-Simons gauge field. These were trying to explain phenomena that were happening at the quantized fractions where there is a gap. And then we extended that theory to see what would happen, what does it imply at filling fraction 1/2 where there's not a gap, and at the very nearby, what happens as you go asymptotically close. If you look at filling fractions where there are quantized Hall states, FQH is a fraction of quantized Hall state, near nu equals 1/2, and this was this paper that I wrote with Patrick Lee and Nick Reed in 1992, which I will refer to as HLR, as people generally refer to it. So what happens there is in this composite fermion picture, or in this fermion Chern-Simons picture, you're attaching basically flux quanta of some artificial Chern-Simons field to the electrons at nu equals 1/2. On average, the Chern-Simons field exactly cancels the external magnetic field. So in mean field theory, you have a bunch of particles moving in zero magnetic field. We, of course, know how to solve that. You get a Fermi sea of non-relativistic particles. But of course, if you go beyond mean field theory, then there are, of course, fluctuations that are very important. There are fluctuations due to the Coulomb interaction, the two-body interactions, and even maybe more important is the Chern-Simons field itself has fluctuations, or gauge fluctuations, and they change things. Now, whoops. Yeah, so okay, so we say numerical calculations show no, so theoretically there should be a particle Hole symmetry that could be spontaneously broken. You could have a phase transition, but there's no indication of spontaneous symmetry breaking at nu equals 1/2. Unlike the 5/2s, where the numerical simulations, even if they're wrong, they indicate that the ground state is either a Pfaffian or anti-Pfaffian, which are particle Hole conjugates of each other. So if that's correct, there would be at 5/2 a spontaneous symmetry breaking. But there's no indication of that at nu equals 1/2. So we expect the ground state to be particle Hole symmetric. And that's nice, except that the HLR theory doesn't look particle Hole symmetric. It looks quite asymmetric, and it has been questioned whether, in fact, it's even compatible with particle symmetry. And if it's not only not explicitly particle Hole symmetric, but actually is incompatible, then that's a real problem for the validity of the theory, because it should at least apply to the situation where you're projected to a single Landau level. And so I'm motivated by some of the arguments that there are problems with particle symmetry. Dam Sung formulated a beautiful theory in 2015, a new theory of the half Landau level, which was based on a Fermi sea of massless Dirac fermions. And his theory is manifestly pH symmetric, and it had some nice advantage. It had a lot of very nice features about it. It made a lot of calculations somewhat simpler. But then the question is, are these two theories equivalent? In other words, is HLR just a less elegant formulation of something that is, or is there actually some fundamental difference? And there has been quite a bit of discussion about that. Well, the current status is that we think they're the same, but we haven't been able to completely show it. What we were able to show, and this is work that I did with Chang Wang and Nigel Cooper and Adi Stern, published about a year ago, it shows that the theories actually do agree for almost all properties. They agree even at the level of at RPA level. And these include a number of properties where it was previously believed that HLR was actually incompatible with pH symmetry. We showed that the those analyses were just not done properly. And what we believe is that, and of course we don't assume that you're projecting onto the lowest Landau level in any way. We don't. In HLR, there is no such assumption. So if this is correct, then we're making predictions that these things should be particle symmetric, even if you include mixing between the Landau levels. That it should this particle symmetry should emerge asymptotically as you go to filling fraction a half. So it's a kind of emergent symmetry. And if that's true, then that would be very nice. But Sohn and collaborators have shown that actually, although all of these things that we showed are particle symmetric, there are other properties where some level of a problem still exists, at least at the RPA level. That if you use this HLR theory at RPA, you make predictions which are incompatible with particle symmetry and therefore must be wrong if the system really has zero mass. And so the question is, well, and the open question is that we haven't been able to completely resolve is, can you recover these if you go beyond RPA? After RPA is just is correct, correct description of what happens to long wavelengths and small deviations, but are these things that we should be able to somehow correct if we go beyond it by including things like vertex corrections? But again, what I mean by RPA level, in RPA is basically random phase particles. Crudely, it's just time-dependent mean field theory. So that you have a bunch of free fermi. We treat these interacting problems, a bunch of free fermions moving in self-consistent fields, which include both the self-consistent gauge field and the self-consistent Coulomb potential, which is usual RPA. But we know that that's only a crude approximation. You always also have to include effective mass renormalizations, for example, which are beyond RPA. And indeed, that's extremely important. You get totally the wrong mass if you just use the bare mass in this limit. So you need to include a renormalized mass. If you have a renormalized mass, then we know you also have to include a Fermi velocity, which is the same thing. You need to include Landau interaction parameters, which go hand in hand with them, and they have to be included properly. When I say RPA level, I assume these are included, and it's not crucial for the properties we're talking about, but that's there. So let me just say something about, so what are some of the predictions that one is concerned with? So first let me review some of the predictions that are made by HLR at the RPA level, which agree with Sohn Dirac. So they're made by both theories make the same predictions, and they're not completely trivial. So of course, the first thing is that the ground state should be compressible because it has a Fermi surface, and of course those predictions could be wrong, such as in the second Landau level where we assume some kind of cap is opening up like a superconducting cap. But at least this is a possibility. Their predictions, if you look at the Jane states, which are the fraction particle states in the form nu is equal to p over 2p plus 1, where p is a positive or negative integer, these describe states for large p, they're very close to nu equals a half, and there's a symmetry between plus a half and minus a half in the predicted fractions, and the relative sizes of the energy gaps close to nu equals a half. In the simplest approximation, they go linearly with the distance from nu equals a half. If you take fluctuations into account, they're corrections. But they're the same in the two theories. The transport in the absence of impurities, DC Hall conductance at nu equals a half should be 1/2 E squared over H. That, of course, is the same. Less trivial, and of course, in the absence of impurities, sigma XX in longitudinal conductance is 0 at long wavelengths. There's no scattering, there's no dissipation. But if you look at the longitudinal conductance at finite wave vector in the limit of omega goes to 0, one of the things we found in HLR was a rather remarkable prediction that this longitudinal conductance, if Q is in the x direction, it goes as Q over 8 pi kf. Kf is the Fermi velocity, which is determined by the density, and Q is the wave vector, so there's no adjustable parameters. And moreover, it's a singular function it depends on the absolute value of the wave vector q. That's this is in the absence of impurities. This would hold at all q. With impurities, it would only hold where q is. That should be larger than the inverse mean-free path of the scattering that you would expect. And this means that, well, so this is a singular behavior in q. That means you have a non-local conductivity. If you hit the system with a pulse at one point, then what's happening is these composite fermions, although they're charged, the composite fermions can travel very large distances up to a mean-free path. And so that means that you have non-local conductivity, and this, in fact, this is measured in these acoustic experiments, and that's what gives rise to the anomaly. And you can see that these composite fermions are traveling distances of the order of maybe 50 times larger than the magnetic length, or the cyclotron radius of the actual electron. So these composite fermions really look very different from the bare ones. Okay, and if you now go away from nu equals a half, then these things don't travel. They now go in cyclotron orbits, and this leads to oscillations actually in surface acoustic waves as a function of the magnetic field, which were observed in 1993. It was a fairly nice confirmation of predictions. Okay, so that's something that did work, and it works in both theories. But now something which was considered a real problem. This dates back actually to 1997, something that Killis and coworkers pointed out. So if you're have exact particle-hole symmetry in a system that's restricted at the lowest Landau level, let's say, and if you have impurities which are particle, if we now add impurities, and we assume that the impurities are also particle-hole symmetric, equal numbers of positive and negative ones of equal strength, then the system is still particle-hole symmetric, and particle-hole symmetry by itself predicts that the Hall conductance at infinite wavelengths, sigma xy of omega, should be 1/2 e squared over h, or 1/4 pi in units, where we set h equals h bar equals 1. That should be true at all frequencies, actually, and also in the presence of the impurities. They would doubt, and at least a simple argument based on the composite fermion theory would make it seem that this would not be correct in HLR theory. So that would say that there's deviations are actually small that you predict if you do the naive. What you find is that the deviations, corrections to this 1/4 pi, which are proportional to the square of the impurity scattering rate. So if the impurity scattering rate is small, that's a small correction, whereas sigma xx is linear. So it's small compared to corrections of sigma xx. But theoretically, if that's a real problem, we have to worry about it, because then there could be some deviation difference between the two theories. So, but our results, we found that that's just because the naive theory wasn't done carefully enough. It's actually a little complicated, but I don't know if I'll have time to explain why. But if you do it correctly, even at the RPA level, but do the RPA correctly, the second order, the effect disappears. That at least the second order, there's no deviation from this particle symmetric thing, and it has nothing to do with whether there's a bare mass there or not. So that says it should be an emergent quantity. And there were several other properties which also people had believed were a problem for HLR because of deviations. And we saw that those also weren't a problem. So one of them is if you look at if we go to a filling fraction where there's a fraction of a full state near nu equals a half, but not at nu equals a half, these are the Jane fractions, then you have a magnetoroton spectrum. The excitation, there's a gap, and inside the gap there are excitations which are based on excitons, and these excitons have a bunch of an oscillating spectrum as a function of Q, and they're minimum in the positions. And if you do it naively, there would be a very small asymmetry between nu greater than a half and nu less than a half. And we found that, well, that's just because you haven't done theory properly. And another, that's very hard to measure experimentally, but then there are resistance, something called Weiss oscillations, which are, if you look at the system in the presence of a periodic potential, you put a grating on with a certain period, which is of the order of, let's say, it might be of the order of 100 nanometers or something like that. And then you look at, and you vary the magnetic field, or vary the filling fraction, you're going to see oscillations in the resistance. You have to have impurities present to have a resistance, and then there are additional oscillations in the resistance as a result of this. Basically, it's something that it crudely occurs because of commensurability between the cyclotron diameter of these effective quasiparticles and the wavelength. And these are called Weiss oscillations. And here, this is what it looks like. Here's the grating. And these are this is actually from beautiful experiments at Princeton in Shayegan's group. And you can see these oscillations as a function of magnetic field with various minima. And we would like to explain those. And so what happens is the following. This is a theoretical calculation. Now, this actually was done, this figure was taken from a paper by Chogi, Raghu, and Mulligan. And they're calculating magnetar resistance in the presence of a periodic potential with some particular choice that the wavelength, wave vector times the magnetic length is 0.2, is a function of deviations from nu equals a half. And you can see in this theory, whoops, yeah, so it's symmetric. You have to vary the density and keep the magnetic field fixed to get the exact symmetry. And the theoretical curve, which they calculated based on Sohn-Dirac theory, is exactly symmetric. And the naive theory of using HLR would be slightly deviate from these by amounts comparable, well, to the width, but small amounts, but not exactly zero. On the other hand, if you do the calculation properly, you get rid of that asymmetry, and we get something where the positions in the middle are exactly the same. And in fact, the curves are indistinguishable on this scale at this level of approximation. There's some approximations that go into it. The experiments are actually, oops. So these dashed lines are the experiments that I showed you before, where the minima actually are. And if you look, you can see that they're slightly shifted from the actual minima by an amount that's just comparable to what the deviation between theories are. But but of course, the deviation is completely symmetric. So the statement is the two theories agree, and they're both symmetric, but there is slight deviation between a theory and experiment. But there could be a lot of reasons for that, and I don't think that's a reason for concern. I'm almost out of time, but so just to give examples of properties where HLR and Sohn-Dirac do not agree at the RPA level. So they pointed out, if you look at the order Q squared correction to the wave vector dependent conductivity tensor sigma ij at nu equals a half in the region, to make this well defined. Whoops. You have to do that for frequencies that are bigger than Q times the Fermi velocity, we normalize Fermi velocity. Or if you look at James fractions asymptotically close to nu equals a half, then omega has to be less than gap frequency. Then particle-hole symmetry makes some predictions or constraints on these coefficients, and they don't come out right at the RPA level. If you do HLR at the RPA level, you don't get things that are consistent. So there are problems with RPA for this particular quantities, and we don't quite know what it is. And we think they have to do with vertex corrections. Vertex corrections mean corrections to the coupling constants between, say, the fermions and the gauge fields, or between the gauge field, between the fermions at non-zero wave vector or that have to be taken into account. In general, there will be such corrections in both. There have to be such corrections both in zone Dirac and in HLR, otherwise you won't be able to calculate all kinds of things correctly. And these, in general, contain parameters that depend on the details of the microscopic model. So then you could adjust them so that you get particle symmetry or not, depending on what the microscopic. So that all seems to work well, but the fact is that we have not been able to actually show that these, to find exactly what the right corrections are and show that they could emerge. So I think this is still an open question. Oops. Okay, so let's see, do I have any, how's my time doing?
So we will have 5 more minutes.
Okay, so let me just say, let me just say something about the origins of these two theories. What, why should there be two different theories in the first place, and where do they come from? So the problem we want to solve, that I want to solve, at least, is a problem of non-interacting, of interacting electrons, let's say, with a quadratic spectrum, so they're not relativistic, in a two-body interaction, in the presence of a uniform magnetic field. And what we did was to begin with an exact, really just an exact mathematical transformation, where you it's basically a gauge transformation, where you're just multiplying the phase of the wave function by a singular quantity, which introduces, since you modified the wave function, you have to introduce a vector potential to get the right kinetic energy, and that gives you this Chern-Simons gauge field. The curl of the gauge field is the magnetic field. It's the fake magnetic field, which is just 4 pi times the density. And treating it mean field theory, of course, you get what I've described. And the hypothesis we made is that, of course, the mean field theory isn't right, but it should be the right starting point, that you should be able to start with the mean field theory and include the fluctuations by perturbation theory. And this perturbation theory should somehow converge, whatever converging means exactly in a system without a gap, and that you should be able to understand the theory by taking these things into account, and that when you did that, what would happen is you could go by adiabatically from the true ground state to the from the mean field to true ground state, and that this would happen without a phase transition, which of course is not necessarily true, but if we assume that's true, then you still retain the Fermi surface. And we said that you should be able to then do some kind of renormalization group-like calculation, and RPA would be the first step along these lines, and then you would get other corrections at short wavelengths and high frequencies, which we didn't exactly know how to do. So Dirac doesn't start from this. It starts, if you wish, it starts from an unphysical model where you had Dirac fermions to begin with, so then you have particle symmetry. But it shouldn't really matter if you're projecting to the lowest Landau level. You shouldn't really care, right? But they don't actually do any kind of. They also don't do a real calculation. It's just an argument. So we don't. Okay. So and then the other thing they do is they introduce the gauge field by a different method than HLR, which is slightly more general. It's maybe more general, but it's approximate, but in fact you can make a mathematical. In this case, it actually doesn't matter. If it's massless Dirac particles, you can really make a mathematical transformation. So the fact that it's different gauge field is not important. The fact that it's somehow Dirac particles, well, the fact that they're two spins doesn't matter either, because you have a finite Fermi level, that there's a Berry phase. There are some differences, and so there is a possibility that they're different. Both theories, I should mention, have infrared divergences, and so that for Coulomb interactions, these effective masses actually diverge logarithmically. There are problems to make to make the whole discussion completely well defined, but they're exactly the same in the two theories, so we don't think there's any problem there. Okay, and as I've said, we've already mentioned, second Landau level is different, and we understand, you can understand the Pfaffian or the anti-Pfaffian, the pH Pfaffian equally well in any of these situations. For example, the PF, the Pfaffian as pairing at angular momentum L equals 2, in the Dirac picture, these just have pairing in angular momentum L equals 2 for Fafkian. Anti-Fafkian is L equals -2, pH Fafkian is L equals 0. In the HLR, it's L equals 1, -3, and -1. So it doesn't look symmetric, but there's nothing impossible about it. Okay, so those are the open questions. Are they really equivalent? And what does it even mean exactly to have two theories to be equivalent in low energy theories? What is it that we expect them to be able to calculate? And what would we say, well, we can't expect a low energy theory to calculate? I think there are open questions.
So in the back of your mind, do you think that the HLR Fermi surface reorganizes itself into a Dirac-like dispersion, or is that too naive?
So I don't think the dispersion matters much, because we're only looking at things that happen close to the Fermi energy, right? So if you're looking at the difference between linear so the Fermi velocity matters, but now if you look at curvature, I don't think that really matters. Now you're looking at higher energy things, and you have to put you would have corrections due to things like the Landau parameters and so forth. And so certainly there are interaction parameters that also would introduce effectively curvature. So I don't think as far as we can see, the curvature of the spectrum is not important, but the Berry phase is a little bit more, the Berry curvature is a little more problematic, possibly.
The density of states is very different.
Yeah, but you don't care about density. There's corrections to the density of states only at the density of states at the Fermi level is determined by the Fermi velocity. Okay, then there's corrections to the density of states, but there are other things that also introduce asymmetries at that level. So I don't think that's, and certainly the curvature is not, we could certainly renormalize the curvature anything if we wanted to. I'm not going to argue that the energy is exactly, in HLR we certainly wouldn't argue that the energy is exactly quadratic. It could be, we could change the spectrum any way we wanted to. I think without much problem, because there's renormalization. So if that were important, I don't think that would be the difference. But if things that needs to be thought about.
One good question.
So along those lines, the claim isn't just that the claim isn't just that the spectrum of a Dirac particle with some chemical potential is different from the spectrum of a non-relativistic particle at some chemical potential, right? Those theories are both the same once you take the non-relativistic limit with the gauge field present.
Yeah. So first of all, the important thing what we're talking about here is dispersion of composite fermions. You can't necessarily measure that. You can't create a composite fermion or annihilate. You only can create pairs, and then these pairs interact with gauge fields. So the composite fermions themselves are not observable quantities. Everything you observe, I would say, would be things like, everything I talked about was the response to an electromagnetic field, or you could measure specific heat, which is a little bit more complicated. You can think about it as responses on a gravitational field or something. But I think it's the density of states. Specific heat matters, but then specific heat, linear order, it's just determined by density, by the effective mass. Plus, if they're collective modes, you may have to add them in as well. Okay, but you're not directly measuring that. It's not so easy to measure the dispersions, particularly since they're going to be life. You also know that if you go away from the Fermi surface, it's finite lifetimes.
What's an example of a property that doesn't just follow from the fact that HLR is the non-relativistic limit of Son's theory? What's an example of a property that doesn't just follow from the fact that HLR is the non-relativistic limit of Son's theory?
Non-relativistic limit
of Son's.
zone. Oh, well,
Okay.
whether zone is, you could turn around and say, can you justify the zone theory because it's, I don't know what you mean by non-relativistic. You could add a finite mass to the zone theory. If you introduce a large finite mass to the zone theory, you would predict certainly the theory becomes more complicated. And if the mass is big enough, it does go continuously over into the HLR theory. But if you calculate something like this, all the Q squared, if you calculate in mean field theory, the Q, it's not obvious that you get the same answer, but let's say you could put a finite mass in, and indeed, one is a limit of the other, but it's certainly not obvious that when you calculate, say, the position of the magnetorotan minima, they're going to be the same independent of the mass you're adding. So a lot of the quantities that we added, that we calculated, that are the same as these two theories, just because one is by non-relativistic limit, you mean actually adding a finite mass and a large, not a small mass, but a large mass. It's not at all obvious that the quantities are independent, and some of the quantities apparently do depend on that mass, at least in our case. So that's the issue that's open.
Okay, I think we really have to move on. Let's thank